This is part 6 in a series of videos in which I'm attempting to design a drop-in replacement for the Fluke 9010A cassette drive. I want to use a solid-state memory, produce small memory cards to duplicate the functionality of the tapes, and have it as a direct plug-in replacement for the original drive. Now, there are some complications when dealing with old equipment like this, as I touched on in the previous video. Now, one approach I could have used would be to just use a similar device. This is essentially an EEPROM version of the device that's in the cassette drive, and then just change the code, attach a memory chip. Couple of reasons I haven't done that. One is because these are quite rare and difficult to get hold of, and no doubt that will just get worse. But also I wanted to be able to show the inner workings of not just the process for doing this, but also how these systems work. And that is the main goal of my channel, is to show the inner workings of systems like this, and how the signals and the original designs were conceived, and how the various parts of the system work together. So I decided to take a slightly different approach. So what I'll be doing here is using a PIC microprocessor. It doesn't matter what you use, a PIC, anything else you want to use, as long as it meets the purpose and you know how to use it. But that is part of the point. It's meant to be fun. This is, as ever, not necessarily the best way of doing this. In fact, it almost certainly isn't the best way of doing it, but it's certainly a very good way to learn how to do this. Breaking everything down into discrete elements means that it's very easy to describe each individual part. If this was a commercial product, then it would be a no-brainer. It would be an FPGA, and I'll explain why that is as we go through. There are various aspects of this that make this quite a complex thing to do, but I'm aiming for a simple solution, and to get a simple solution for a complex task means properly understanding that task, and you can then make a much better job of getting a system up and running with minimal effort. So before we go into this and look at the basic operation I've got going so far, we'll have a look at the firmware that runs in the control device on the original cassette drive, and that will give us a good starting point for discussing how to go about designing the replacement. So I'll get the Fluke out of the way, and we'll spend a few minutes going through the firmware. If you're not interested in the firmware for the original device, then just skip forward to the point where we get back to the hardware design. In a previous video I described how I'd gone about writing a decompiler for the device that's in the cassette drive. The one I downloaded didn't seem to work properly. Incidentally, I also started off with a file for this drive that I downloaded off the internet, and as it turns out there are some errors in it, so what I ended up doing was reading the actual device on my drive, and then I used that as the file to pass through the decompiler, and that's the file that I ended up using here. So I've been annotating it, going through, trying to figure out exactly how this works. I did this in conjunction with the logic analyzer. I won't go through this in huge detail, I'll just go through the basic details. But if you do want me to go through this in more detail, then leave a comment. It would take several videos just to go through this in detail, so I'll skip through most of it. I'll just go through the important points. But what I'm trying to do by going through this is to figure out how to go about designing the replacement hardware and firmware. So I need to understand exactly what's going on in here in terms of the interface with the 9010A. Now, the first thing we know is that there are at least 3 command values that we're interested in. That's 11 hex, 12 hex and 13. So we know they're read, write and stop. There are other commands as well, but because we have those as starting point values, and we know that if we do come across those values, then potentially they are command values, but they might not be in that form in the source code, is the only thing to bear in mind. We also know by looking at the data sheet what the formatting of the data is going to the cassette, so we know there must be a block of code in here that takes data values and encodes it in this form, and also another block of code that decodes this data stream coming from the cassette. We won't need those in our final version, but knowing that they exist means that we can at least try to make some sense of what's in the source code. So I've mostly finished going through this, and what I've been doing, I've been creating, and again this is partly done in conjunction with the schematic for the cassette drive. So I've been going through figuring out what each of the pins does, what each particular value is for, and then figuring out what the various flags are within the 8041 device. The 8041 is a bit like a PIC. It's got a processor core and a few peripheral registers, inbuilt flags, that sort of thing, and we'll come back to the general way we will be duplicating its functionality later in this video. So the first thing to bear in mind is it has a reset vector of 0, so we start at this point, and the first instruction was a jump to address 31. So what we can do is say, well, this is where the start of the code is, and then that generally means that everything between the reset vector and this point is going to be something more specific. So what we have here are some there's a block of code for an interrupt handler, and also two sets of vectors for jumps, one for vectors within the current bank of memory and one for vectors outside of the current bank of memory. The 8041 is a banked device, so certain instructions can only access addresses within each individual bank, and other instructions can jump across the entire memory space. And so that's why we have this sort of two-step arrangement for vectors. But like I said, I won't go into too much detail. If you want more on this, then let me know. But what we end up with is when we get to the start address, we can start going through the code and see what it's actually doing. And the first block, as we might expect, is just clearing various registers and preparing the device, and part of that will be to reset the hardware into a known state. So as we go through, then what I'm doing here is breaking it into blocks of code to see what each one does, and we can see here that we have a call to a particular address. So what I can then do, obviously this is not here when I start, it's just the raw code, and when I wrote the assembler or the disassembler, then I used text very similar to what was in the datasheet. So if we now jump up to address 035E, then that will give us what we know is a point within a function. And I went through that to see exactly what it was, and it turns out that it's a function that causes the drive to be put into a known state. It's kind of like a drive wait, but it leaves the drive in a particular state, and in this case it effectively turns the drive off and tells it to go back to sleep. So it turns all the hardware into the default standby mode, and then we keep going down until we get to the return instruction. There are also some other jumps in here, but they are kind of within this block of code, so it doesn't go anywhere else. So we can then go back. So once we know what that block of code does, we have a function defined, and we can then search through the rest of the code for any calls to this address, and then we can document them as calls to drive wait one function that we've defined. And if we keep going through, we can just unpick it, looking for calls, see what the call goes to, figuring out if it's a function, and what we end up with is a set of functions that are in different parts of the code. So we have a delay 1, it's a short delay, consists of a series of knobs, and when this is called, register R3 contains a count of the number of times this loop is gone around. It's a familiar construct if you write assembly code. And we know that it's using R3 for this because we've got a decrement jump not 0 at the end or towards the end of the function. And this just causes it to decrement R3 and jump back to the start, until R3 becomes 0, in which case it will exit the function and jump back to where it came from. We have the drive wait 1 that we saw. We then have a function that reads a data byte from the tape, so that is, it essentially decodes the data stream coming from the tape, looking at the data input pin that we derived from the schematic, and then that's followed by the reverse, where a value in R2 is used to encode data onto the tape. So we can then eliminate the last part of the code block, so we know what all that does, and again we can search through for instances of calls to those functions. In other words, if we look for calls to the write data, then we can be fairly certain that we are in the block of code that writes the data to the tape. And conversely, if we look for calls to the read data, then we can be fairly certain we're in the loop that reads the data back from the tape. And that's what I did. I just went through looking for these loops. So the device just loops around this main part of the loop, waiting for a command to be received from the 9010. When a command is received, it does a bit of checking to make sure it's within certain limits. If it's not, then it aborts the command, and it also continually checks the status of the cassette, which we'll come back to later on. And if the cassette's not present or not in the right mode, then it again will abort and it won't proceed with the command, and it will return an error value to the Fluke. Assuming the checks work and there's no issues, we get down to this instruction, jump at A. And what this means is it's quite a powerful instruction. It causes the execution to jump from this point to the address that's stored at the memory location pointed to by the accumulator. Sounds quite complex. What it means, for example, let's assume the accumulator has a value of 11 hex, which is one of the instructions that the Fluke can send. The accumulator has a value of 11 hex, so the processor will load the value at that address into the instruction pointer register, and in this case it's 11 hex, turned out to be a data byte of course. We have a value of 78, so that will cause execution to jump to address 78. So in other words, it will jump to here, and that's why I've headed this as command 11. If the value was a 12 hex, then the next instruction to be carried out would be at address 9. And so if we go back and look at address 9, which is actually just up here, we'll see that that is an instruction to jump to address 100. The reason it can't jump directly is because that particular instruction can only jump within the particular bank it's in. It can't jump across banks, whereas this jump can. So it uses this value to jump to here, and then it jumps from here to address 100. So if we go to address 100, then you can see I've headed this read tape vector. So this is the loop, or the start of the loop, where the tape is read. So this is the way I went about this, just looking at the various commands. So we know there are various commands we need to be searching for. More importantly, we know that we need our system to be able to pick up and deal with command values coming in. And they come in on essentially 4 registers. We have an incoming, on the 8041, we have an incoming data register, an outgoing data register, an incoming command register, and an outgoing command register. So now we'll look at the hardware design that I've come up with to duplicate this, and we'll then start looking at how to implement this in terms of a replacement for the cassette drive. Like I said, if you want me to go into this in more detail, let me know. It does get fairly involved, but as I say, we're not that interested in this or most of the detail. We're just interested in the main flow of data that this gives us, but I had to do this to figure out what that flow of data was. Okay, so this is the general design I've come up with for the replacement device. Now, this is not the only way you could do this. There's probably an infinite number of different ways you could go about designing something like this. And this is actually quite a difficult way of doing it, so it's not a particularly good way. But it's a very good way for me to explain how the individual parts work, so this is why I've chosen this approach. So what we have here are a series of data latches. So these are 8-bit data latches. So in this case I'm using 74LS574s, and what we're using these for is we're using a microprocessor here as the interface, the control element within our device, but we can't hook that directly to the bus from the Fluke, even via a buffer, simply because the response we would get from the processor will be too slow. The way that the interface works when it's talking to the control device on the original drive is the Fluke will assert the chip select line, and then it will expect the data to immediately appear on the data bus, or it will try to write data in to the tape drive, but it won't sit and wait for an acknowledge. It will just assert the required control signals after it's placed the data on the bus, and it will expect the device to immediately read it. Now, you can't do that with a microprocessor based system because it's going to be busy doing something, and even if you use an interrupt, then by the time it's got into the interrupt and pushed a few values onto the stack, then it's taken probably half a microsecond or so, and by that time the Fluke's gone off to do something else, and you've missed the data. Or the converse would be true if it's asserted the chip select line and it's trying to read data. By the time you've got round to putting the data onto the data bus, the Fluke would have got bored and gone and done something else, and it would read the wrong value. So the way this works is the processor runs away in the background, and whenever there's data to be presented, it will preload it into the outgoing latches, and then the way that the Fluke will access this is it uses 4 control lines. These come through a decoder, and the way I've got this arranged is the particular line on the decoder will be used to put the contents of the required latch onto the bus. Because this is kind of a hardware function, then it will do this immediately, so there's only a few nanoseconds delay, and then whenever there's different data, then the processor can load it at its leisure into the required latch. And the same thing with incoming data. We need to do something similar. The difference here is that the data is latched into here under control again of the decoder, and also we have another smaller latch down here, and the way this works is incoming control line information is latched into here, and then the processor can look at it on a regular basis, check to see what commands need to be carried out, and it will then, for example, load fresh data into the latches. There's quite a long delay between individual events, simply because although when the Fluke looks for data it doesn't wait very long, it has to process data it's just read, so there's quite long delays, plenty of time for us to do this. I have the processor running at 48 megahertz, so it's quite responsive. It can certainly run a lot faster than the original. But this is very akin to the way that the original worked. It was really a processor with a series of latches that interfaced it to the outside world. And you have to do this if you're using a microprocessor. If we were using an FPGA, we wouldn't have to do this because an FPGA is effectively a parallel device. But it wouldn't be in keeping with what my channel's all about. I want to go through the basics of how all this stuff works. So once we've got this basic design sorted out, we can put it onto a breadboard and start testing it. The only complication down here, of course, is knowing what particular incoming control signals we have to respond to. And that's quite straightforward. That was just really a case of writing down what the command line status would be for any given instruction type, and that will give us a binary value. And then we can look up in the data sheet for the decoder which particular line will give us the output of the binary value. One slight additional complication is in the sense and the timing of some of the signals, which is why this buffer's here and why this one's here. Okay, so I'll get the Fluke back onto the bench. We'll have a look at the hardware as it stands at the moment, and we'll go from there. Now, of course, if you do something like this, you need to be fairly careful. You don't want to damage the Fluke, so you need to be very cautious in the approach that you take. And what I've been doing here is making sure that this works the way I intend it to before I plug it back into the Fluke. And one other thing I would point out is this currently doesn't have an input buffer. I mentioned that's fairly important. The devices I'm using are kind of like buffers, but even so, the final design would have an additional buffer on the interface between the cable and the device itself. But I'm not using that at the moment. So what I have here at the moment is pretty much what I've got on the diagram. I've got the series of latches. I've got a microprocessor here, and I've got an interface I can use to develop while connected to the PC. So I've got the ICSP interface connected here, and it means that I can develop this on a debugger, so it makes it a lot more straightforward. Got it standalone at the moment just so I can demonstrate it, but it does mean that designing it like this gives me far more scope for getting it right. We then have the decoder, which gives us the control lines for the various devices, and then we have the additional latch here which latches the control lines. It's not all complete yet. There's still one latch missing. I don't have the latch at the top. We don't need that for this phase of testing. One other point I'd make here is when you're using things like latches and they're attached to a common bus, you need to be absolutely certain what state they will come up in when you power up the device. And if you're using something like a microprocessor, a PIC, an AVR, something like that, then in general the pins come up as inputs until they're configured by the source code that's running in the device. And so you need a pull up or pull down resistor to make sure that any lines that will come up as inputs that need to be in a certain state are properly handled in a proper state when you power this up. You don't want, for example, the 3 or 4 inputs to your latches all floating and being ambiguous when you first apply power. That could actually stop the processor running, so you can't rely on this getting going quickly and correcting it. You need to make sure that from the hardware perspective, without the processor running, that everything's going to be fine. And the same is true on the outward facing side. You need to make sure that everything comes up exactly as you intended to, and it doesn't prevent the Fluke from booting. Okay, so we've got this connected up. The way I've got this configured at the moment, I'm just doing some basic testing. We have an LED down here that responds in theory when it goes into either tape read or tape write mode. And what I'm trying to do here is just properly develop the interface to make sure it works. There are some complications. The Fluke will issue a command and then it will immediately check to see if the tape is in a state where it can be used. And the way I've got this arranged is it automatically takes care of any error handling within that. So I'll come to that in more detail in a future video when we look at the source code for the processor. But for now, the way I've got this arranged is this lead essentially it duplicates the cassette present switch on the original cassette. So if we move this, it should give us a no cassette error on the Fluke if this interface is working. It's not just reading a single line. This actually goes through the processor, and the codes are sent as a full byte that the Fluke interprets. So there are no single control lines going in and out of this device. Everything is transferred through the data port. Other than that, the way that I've got this set up is it's looking for the command values. That's either 11 hex, 12 or 13, and in theory it should be able to respond to those three, return the correct code to the Fluke, and then the Fluke should go into the correct mode to run that command. It's not going to read or write to memory, of course, because I don't yet have the memory attached to this. That's ironically enough one of the last things to be done, but it should go into the proper mode, and the Fluke should identify that as the proper mode, and it will just start continually sending data if it's writing, or continually trying to read data if it's reading. It's fairly dumb in that respect. It doesn't do a lot of fault finding. It just waits for the end of file commands to be received. Okay, so I'll power it up. Firstly, we're looking for the Fluke to power on at all, and as we can see, it does. Apologies for any flickering. As ever, that's not present in real life. That's just because of my camera shutter speed. Notice this LED is off. The one in the corner, if you can see it, is just power. But what should happen now is I've got this in the cassette present position. So if I press, for example, read tape, then we should get a message asking us if we want to actually proceed. That might not sound like a big step, but you have to have a lot of this working before the Fluke will do that, because it's a multi-step process. When I press the key, it will send the command, and then it will immediately read back a value for the status of the cassette. So if I press read, you can see it saying, are we sure? So we know that it's already transferred several bytes of data between this. If I say no, the Fluke aborts that. I'll now change the position of this jumper, which is effectively the same as removing the cassette from the original drive. We will be using this feature because we want to know if there's a memory card plugged into our memory reader. I can't change the message on the Fluke, but it will come up with no cassette if we have the jumper in this position. So what will happen now is the command will come from the Fluke, the microcontroller will return the error code to say that the cassette is not present, and that should be represented on the Fluke with a no cassette message. So as we can see, it's now saying no cassette, and it will do that whether we're trying to read or write. If I put the jumper back, then it should go back to the correct message. I would say at this point the processor has already loaded the correct value into the latch. It's just the latch is waiting there to be read by the Fluke. Like I said, it wouldn't be fast enough to do that in real time, so this microcontroller is constantly going around doing all the housekeeping, loading the registers with whatever value is current, and that's the value that the Fluke will then read. So if I press the read again, you can see it's saying, are we sure? If I say yes, then this LED should come on if it's detected the command, and we should get a message on the Fluke screen saying that it's reading the tape. So as we can see, it's reading tape. You probably can't see it, it's quite dim, but the LED is now on. I'll stop that. In fact, we'll reboot the Fluke, make sure it boots up, and this time we'll try a tape write. So exactly the same thing. If I press write, we get an are you sure? If I say no and effectively remove the cassette, try it again, we get a no cassette message. I'll put the cassette back in, write the tape, yes we want to continue, and again we're now getting a message on the Fluke saying it's writing the tape, and at this point it started transferring data. Currently the microcontroller is not picking up that data. That's the next step, and that's just really a case of handling the data coming through this buffer, writing it into a memory chip, and then doing the reverse when it's reading the data. So that's how far I've got. It seems to be working fine. It's not interfering with the operation of the Fluke. So the next step is to get the reading and writing sorted out. I won't be reading and writing to a memory chip just yet. The next step is just to get the data to transfer in both directions. But this is the main hurdle overcome now. We've got the timing issue sorted out to make sure that this device can actually put data onto the Fluke data bus in a sensible way, and also that it can read incoming data from the same data bus, again in a way that doesn't interfere with the operation of the Fluke. So any comments are welcome. If you think you're going to be interested in something like this, then let me know. And so in the next video we'll start looking at the actual data transfer between the two.